All right, sorry guys for the delay. Let's get it started today. So last time, if you remember, we were talking about some example of basic Bayes rule, and we're using the breast cancer example if you remember what we did, the screening, in particular the screening example. So let me bring that out for us. So for today's lecture, we will so this is where we stopped last time, and this is the case that we're hoping to get an idea of the basic inference procedure. And we were looking at an example of the breast cancer screening test. Like, so before you start taking a test for a particular person, the best guess that you might have for whether this woman has breast cancer or not is the population statistics that you can get. So that's expert information that you can get. So remember, I think it's 1.7% out of the population. So that will be your prior before you start taking the test for this particular woman. And then you're going to receive some test results. So in this case, it was a positive or negative result. And we also have some specific information about the test itself, false positive and false negative, those kind of information. So we are able to use that information as data to update our belief about whether this woman has breast cancer or not. So we use that data to update, and then we come to the point where we have a posterior probability about the belief of whether this woman has breast cancer or not. So, and then we actually did it sequentially, remember? So for the first round, if the woman has a positive result, we actually updated, I think, from 1.7% to 12% for this particular woman if she has positive outcome. And then we were deciding, well, 12% might not be high enough to actually declare whether this woman has it or not. So we might want to do another test, remember? And then if the second test comes in, actually before the second test starts, we're actually going to use the previous posterior, which we believe now will be the new prior for the second test. So now starting from the second test, we have a 12% prior probability for this woman having breast cancer, and then we do the second test. And we experimented with the second test to be positive again, and that gets us to 52% of the posterior probability for this woman, right? So we did this sequentially, and I said you can keep doing it, and of course the posterior probability is going to depend on what kind of data you get. The results that we showed last time was 2 tests in a row come out to be positive, right? So it's possible that the second test is negative, and then you're going to adjust your posterior probability for that event again. And then, so that will be how the sequential updating can be done. And then we came to this point that this slide at the moment we show on the screen right now, that first of all, for Bayesian inference, we want to take advantage of prior information. For this case, the first test, the prior was the previously published study of the results, right, 1.7%, right? And then actually for the second test, to take the advantage of prior information is not only that 1.7% of the population has the breast cancer, but also this particular woman has a positive test result for the first test, right? So we need to use both of those because now we know more than just a randomly selected woman from the population. And then you do it sequentially. So make sure that if you have useful prior information, make use of them, and then the Bayesian inference procedure will allow you to incorporate that in your inference. And the second point here is the Bayesian inference naturally integrates data as you collect it, so that's what we call it as sequential updates. For this particular example, sequential updates make sense because you get one test at a time, right? But then some other times you might get a lot of data points at the same time. So, but nevertheless, you are able to use the data as you collect it if your data collection procedure allows you to do that, okay? So that's the second thing. And the third, some of you actually came to office hours afterwards to ask about like how important it is to know about the frequentist paradigm for this course. So again, in the introduction part, most of the last lecture and today's lecture, I'm hoping to bring your attention to the differences between these two. But again, if you haven't taken much courses or none of the courses you have taken, are related to frequentist statistical methods, don't worry too much. This is the only, like, these 2 lectures will be the only time that we talk about them and then contrast them. And then from moving on, we're going to focus on the Bayesian paradigm. Okay? But still, I want to emphasize the biggest difference, at least to start with, to look at Bayesian inference and frequentist inference. So remember, last time we mentioned the idea of p-value, and we talked about what does it mean to have a p-value of, say, 2.5% or 5%. It is really a counterintuitive definition in a sense that you have to make the assumption that null hypothesis is true, and then conditioning on that, what's the probability that you observe something as extreme as what you see in the data, okay? So, and then following the same idea, the confidence interval that we usually use in the frequentist statistics methods is also, in a way, counterintuitive because it's not really about a probability statement of the hypothesis itself, right? It is about, say, if I do this experiment like for a number of times, then say 95% of the confidence interval is going to cover the truth. Okay, so these 2 are related, and there's always given the assumption that you have to assume that the null hypothesis is true, right? So that's what usually the frequentist approach is about. However, for Bayesian inference, remember we start with the probability of a hypothesis that's prior, right? And then we integrate data, and then the posterior is a conditional probability, which is more intuitive, at least to me, I think, is that given that you observe this set of data, what's the probability that the hypothesis is true? Okay? So you're really making a statement about the probability, not the other way around. Okay? Sorry. You're really making a statement about the probability of the hypothesis, not the other way around. Okay? All right. And we also talked about last time, I think, about like how useful a prior will be, and then especially if 2 people start with 2 different priors, would they ever achieve the same conclusion in the posterior? So last time we talked about this general idea, and I gave the example of, say, even if 2 people have vastly different beliefs in the prior of an event, then as they collect data and they use the same set of data, especially as the data amount grows, then the effect of the prior on the posterior will become less and less. Okay, so eventually the data are going to dominate. Okay, we will see in examples and homework questions how that actually makes sense. But intuitively, get the idea that that once you observe more and more data, then the prior effects will be less on the posterior. Because after all, the posterior is a combination, some kind of combination of the data and the prior. Okay. So, but that also tells us a good prior will help, bad prior will hurt, but the prior matters less as the more data that you have. All right. Okay, so this is just a quick recap of what we did last time, and I know some of the examples might not be most straightforward to a lot of you, but we're gonna have homework questions to touch upon those, so don't worry, but make sure that you do them. So as the introduction, the third topic that I want to talk about is just talk about a particular example of Bayesian inference using us as a data collection procedure I will show you in a minute, and then demonstrate using your R program to show you that Bayesian inference, especially how to get from the prior and the data to posterior, is nothing too fancy. You can do it by hand if you have the patience, but a lot of times statistical programs will be able to help you to do that. So we're going to do a demo and then do a quick probability review of the material that I think will be useful. And then if we have more time, we can start start the section on Bayesian inference for proportion. All right, so I think this will be the last slide about frequentist, so don't worry. One last comparison over here. So both frequentist and Bayesian aim to use the data we use capital Y to learn about the unknown parameter theta. Okay, so theta, let's assume one parameter in the model, but you can have multiple. Right? Okay, so on the left, I presented what frequentist statistical approach usually means. So what you're doing is, as you can see, so it's the probability of the data given the parameter. Okay, so the basic assumption in the frequentist approach is that the parameters are fixed over here, and data are the repeatable random sample. So that's why a lot of times people emphasize that you have to repeat the process multiple times or even for an infinite number of times, then you will be able to get those statistical results. Okay, so what they claim, the basic assumption that the parameters are fixed and data are random. Okay. On the Bayesian paradigm, as you'll remember, that we actually, for a hypothesis, for example, we're gonna put a prior probability on it, and then in terms of parameter in models, we're actually gonna think the, I should say over here, the second point, the parameters are unknown, and then you're trying to describe it probabilistically. So that's why you see that. So this term will eventually be the posterior, as you can see from what we saw earlier. So in the past, we have y to be the data, right? And then theta to be the, in place of theta, we have the hypothesis. But now we're looking at parameters, and then that's how you get the posterior, which means that you're looking at the conditional probability or conditional distribution. Later you will see that the parameter given the data. Okay, so in this way, data are considered fixed, and that's the only data set that you can have. Whereas in the frequentist, people assume that you can repeat this sampling procedure multiple times, and then y is just one time that you get it. Whereas for the Bayesian approach, y actually fixed, you're not able to get anything more, and we're trying to use the information from y to make inference about theta. Okay? So before we move on to next, I do want to just write one more time over here, focusing on the Bayesian approach that we wrote on this slide. So the general procedure, as you might have guessed, is we're curious about theta. Theta is the parameter unknown. Okay, we're trying to make inference about it. And as you can see, the prior on theta will be some probability or some probability distribution that we're going to put on theta before we observe any data, right? And then we're going to collect data. So let me just write the second stage. Okay. And then usually you will see that we will learn different models for the data is that you're going to have some probability distribution of the data given the parameter. Okay. To give you an example, last time we were talking about flipping coins, right? Flipping coins and then count the number of heads, right? And then the data, say in that case, is 0 heads out of 3 tosses, I think, right? And then if you have a parameter, unknown parameter, say, is the probability of getting head when you flip the coin, then that y, little y, equals to 0 out of n equals to 3 out of 3 flips. This will usually be phrased in the binomial distribution, right? We talked about it last time. So this is an example of a parametric model for a, say in this case, a binomial experiment. Okay? So throughout the course, we're going to learn different parametric models that you can give for this data portion. Okay? But it's important to realize that the data y is conveyed through a parametric model given the parameter. Okay? But the parameter is unknown, and that's what we want to know. Okay? And lastly, combine these two together, you get to posterior. Okay, so we're going to go through the Bayes rule later for this specific case, but what you're going to get, as you might have guessed, is this part, right? So now it's given the data, what's the probability or what's the distribution of the unknown parameter. Okay? So as you can see, we need few pieces of information to do any kind of Bayesian inference. So first of all, what will be the prior that you give to the unknown parameter, right? You need that part of information. That's what we're going to learn what you can do. The other part is what's the parametric model that you're going to have for the data, right? You need that as well to compute your probability. And then lastly, how to combine these two into 3. Okay? So we'll see how things can be done in a small example in a minute. But I do want to show you that this general representation is pretty is a generalization from what we saw earlier about the hypothesis and data. It's just in the past, it's a single hypothesis with expressing belief probability statement about it. But now we're moving towards modeling in a way that we actually have parameters in the model, and we want to make inference about the parameter. And what we know is we actually think the parameter is random and unknown. And we're going to put distribution on it. Okay? You start with prior, you combine with data, and then you come to the posterior. Okay? So the key here, as you can see, is theta is unknown and random, and we're going to try to describe it probabilistically through a different kind of statistical distribution. Okay. All right, that's good. Okay, so biggest difference. And so this is what I was talking about earlier, that if you have this binomial experiment, for example, then we will have the unknown. So theta in the binomial will just be the P, the success probability, right? And then that will be your parametric model for your data. And that's what we're actually going to do in the probabilistic models that we talked about. And before the sample is collected, the data is unknown and the theta is unknown too. But once you start to collect data, you'll be able to know what it is. And then from the parametric models that you have, you're able to claim something called model of data. Okay. So we're going to see the example in a minute. But again, make sure that you understand for Bayesian approach, thetas, which are the unknown parameters, you try to describe it through probability distribution. And then from there, you also have some data model, and then combine this two, you're able to get to a posteriori. All right, so maybe it's easier to talk about a concrete example instead of talking about the big picture. And lastly, before we go to the example, let me just summarize it really quick again. The prior distribution is what we see is the distribution for theta before you see anything. So that's the marginal distribution over here, prior. And the sampling model, we talked about the choice of binomial. And we're going to see the example in this case, but you can have many other distributions as you see fit in the way that the data arises. And then the posterior distribution using Bayes' rule, if you remember. So this was the Bayes' rule that we saw before, remember? Right? We are using A and B as more generic as events. But this, again, in this inference procedure, theta, y, they are all in the right place for conducting posterior distribution calculation. And then last time, especially with the breast cancer screening example, we already used something like this, except it was discrete in the denominator, remember? Because it's either you have the test or not, either you have the cancer or not. And then we'll be able to get the marginal probability of the event given that. However, more generically, we're using integral, because a lot of times the parameters can be continuous, and then you'll be able to do some integration in order to get the marginal distribution of y. Okay? In the past, what we saw was for the breast cancer screening was, I think we're just trying to get the probability of someone has a positive outcome, right? So remember, back then, someone has positive outcome is the sum of has positive and positive, I should say, positive test results and having the cancer, right? And we do that as also no cancer. Remember, we tried to compute the joint probability of these two and sum them up in order to get the denominator, right? We were able to do this because the events are discrete. You only have two outcomes over here, right? But more generically, like I said, we use the integration form over here because theta itself might be continuous. and this is more generic. Okay? So a key point will be how would you able to compute this marginal probability. Okay? For the breast cancer testing, it was like a little bit tedious at the beginning, but once you get the gist, you are able to do it. You just like keep computing all of the joint and then collect the correct terms and add them up. But then, even if you have a partition, now it's the partition of 2 events, right? Have it or not have it, like cancer or no cancer. But if for some events we have a partition with like 10 different groups or even 20, then the computation already gets pretty complicated, right? Even though in theory you can still do it. Yeah, so that's the key. And then moving forward, when theta itself becomes continuous, then you might have to do some integration technique to make this work. And then that's where the computation techniques are pretty important in Bayesian inference. And as we go along, we'll see some kind of approximation or some kind of sampling mechanism to make it work. Okay, so let me just use a concrete example now so we know what you can do with it. So, for example, I want to know about the percentage of all VASA students stay up at least one night to get schoolwork done last academic year. I don't know what the percentage will be. It's a parameter of interest, and I use a small p to represent it. Okay, it's unknown. Right? For Bayesian way to think about it, I don't know what it is, and I try to make inference about it. Okay? So naturally, you would think, okay, in order to make inference about p, especially from the Bayesian approach, like we talked about, you get a prior, you collect data, and then after a posterior. So the way that we can think about p here is, okay, before we collect any data, I might have some guesses about p, right? I might have a distribution, or let's just say probability statement about p. So we're going to come up with that as a class in a minute. Okay? So that's for the prior part. But the data part, what should I do? So here I gave the example that later, like soonish, I will sample 10 from us and then just ask you whether you did it or not. And then that will be the data that I collect, right? And then ultimately, we're going to see how you can use the prior that we come up with as a class, and then use the sample of 10 people in our class, and then to come to the posterior inference for this p. Okay. So inevitably, you see that we have to come up with the prior. Okay. So prior is some probability statement about p. P is a percentage. Percentage of VASA students put an all-nighter last academic year. Okay. So we might want to think about how we want to describe p. Okay. And then second is how I'm gonna get this particular data from us as a sample, as well as how to use a probability model to express that data, right? Remember this statement that we talked about, that we start with p, and then we have data given p, right? We need to have a probability model for this. Okay? And as you can imagine, because p is the percentage of all VASA students did put an all-nighter, and then if I get a sample of 10 people, and then I will get, say, for example, 5 people say that I did that, then it's actually a natural binomial experiment, right? Again, because for everybody, I assume that the person have a p probability of putting an all-nighter, and then the number of people actually did it out of a sample of 10 will follow binomial distribution. Okay? So we'll see that in a moment, and then also see how to arrive at the posterior probability statement. Also, it's super important to note that we will build a simplified prior distribution. You will see that soon. And also, make sure that the assumption that when we take the sample, like 10 people from our class, it's actually not a representative sample of the VASA student body. So this is an incorrect assumption, but we're going to do it for now. Okay? But for any statistical model or inference you're doing, it's super important to notice whether you have any kind of limitation. All right, so the way that I'm going to use this is I will ask the whole class to construct a prior distribution defined by the consensus of the class. And then I'm proposing, so P, remember, is the percentage of bachelor students putting all-nighter last academic year. And I'm proposing 11 different numbers for you to choose from, okay? And I asked you to choose just one of them by raising a hand when I'm asking for it. And I'm trying to use this as a way to come up with the prior distribution. So let me explain it one more time before we start. So P is the percentage, right? And then here I'm presenting 11 possible values. But that's not yet the prior distribution. The prior distribution not only should have the values of P that we are choosing, and also the probability that we assign to each value. Otherwise, it's not useful, right? Otherwise, say here, what I'm presenting without looking at the equation marks over here. Here, I'm just proposing 11 different values. I'm asking us to work as a group to come up with the prior distribution for P. Because a distribution does not only have, say, for P, here, not only the values that P can take, but also the probability associated with each value that P can take. Okay? So let me just count how many we have in the class, and I'll ask your guess. Okay? Okay. 19 for us, and I will say, okay, yeah, since the remote student is not from Vassar, let's just have us to guess what it is. And okay, so it's 19 of us, and I will call for who thinks P should be 0. Okay. 0.1. Everybody has to make a choice, by the way. Okay, no. 0.2. 1. Okay. 0.3. 1, 2, 3, 4, 5, 6, 7. Okay. 0.4. 1, 2, 3, 4. Thank you. 0.5. 1. 0.6. 0.7. 2. Okay. 0.8. 1. Okay. 0.9. And 1. Okay. Let me make sure that is 19. Yeah, it's 19. Okay. All right. So what I just wrote down is the counts, right? And then we divide it by 19 to get the probability, right? All right. So obviously, I'm not going to do the mental math here. I will just write it down, and then I will put out a pre-written R script, which is actually on Moodle if you want to test it out later. And I'm going to use that to compute the probability. Okay, so posterior probability, I should say. So give me a second, and I will join the class with the. Yeah, I'll join the. Okay, I think we're still. Okay, all right, so let me see. Okay, just need to make sure that I understand all of this.
Professor,
Yeah.
I step up real quick.
Sorry?
I step up.
Oh, sure. Yeah. Thank you for asking. Okay, so here is my R studio. I think everybody can see it. All right, so we have, oops, I might have to ask you to, sorry about this. Let me, because I think I exit the meeting, so I have to just ask you really quick again about your choice. Sorry about that. So what I'm trying to input is the counts of different choices. And let me ask you really quick again. Sorry about that. And I remember you guys.
I have all of them written down.
Oh, perfect. Thank you. Can you just tell me?
Yeah. 0. 0. 1. 7. 4. 1. 3. 2.
Yeah.
1.
And 0, 0.
Yeah.
Okay. Awesome. Okay. So what you can see here is that I first of all put prior values. I created a vector to include all of the prior values that I think for p. Okay, it goes from 0 to 1, and with increment 0.1. Okay, so it's 11 values. And then I create another prior, I should say, a vector to record the probability that we, as a whole class, come up for this. So it's this vector that we just inputted just now. Okay, so now is the time that we're gonna get in the data. I'm just gonna ask randomly 10 people from our class. So I think I will just do the first 2 rows plus Daniel. Okay, if you don't mind. All right. So 5 here, 4 and 9 and 10. Okay. So just let me know. Did you put an all-nighter last academic here? If you did, just raise your hand. 1, 2, 3, 4, 5, 6, 7. Okay. Thank you for being. Okay. There. Everything stays in the classroom. Anyway, so this is the data, right? We get y, which is the outcome. That's the number of people actually did have an all-nighter last academic year out of 10. Okay, so that's why I'm recording this in this way. All right. So there are some details in the code that is trying to compute the probability step by step. So I will show you in a minute on my iPad, but before we go there, I want to run the script really quick and show you what you will usually see, okay, if you're doing this kind of computation by yourself. So first of all, you see that the final matrix that I can report. Can you see the whole screen? Roughly? Okay, yeah. So the first column is the prior values. Remember, it goes from 0 to 1. Okay, so we have 11 rows. And then the prior probability is computed for us directly. And then now we compute a posterior probability based on, I will show you the details in a minute, but then we're able to come up with a column of prior probability for each values of p, and then the posterior probability for each value of p. Okay? So again, we make the simple assumption that p can only take 11 values. Okay? And then we also collect the data from us as an experiment. And it's important to see certain limitation of the way that we're doing it. But to demonstrate the idea, you can see that we will be able to compute the posterior from it. And I do want to plot it for you really quick to see what's the effect. Okay. So if you can see the plot over here, so that's the value of p, okay? And then I use the red dot, red circle, to represent the prior probability at each data point, not data point, each prior value. And then the cross, blue cross, as the posterior, okay? So as you can see, so before we move on to the technical details of how to do this, let's understand this plot a little bit better to see how the belief is being updated from the data. Okay? So look at the red circle for now. The priors we can see, I remember, like p equals to 0.3 was the highest, like 7 out of 19, right? So you can see that that's the peak. And then like it goes up pretty quickly and then gradually goes down with some up and down over here. And the posterior, as you can see, actually has the highest around 0.6. Okay? And then going down slowly on the right-hand side, and then going down pretty quickly on the left-hand side, right? So think about this a little bit. So here, this is what the posterior tells us and what the prior tells us. And remember that to get the posterior, we do also include the information from the data, right? What did the data tell us? We did, yes?
A lot more people pull all-nighters than I thought.
Yeah, more people, and specifically it's 7 out of 10, right? So in that sense, it's not too surprising that in the posterior, because posterior is trying to combine the information from the prior and the data, and in particular, it looks like the data actually plays a more important role over here, because you can see that the posterior has the highest point around 0.6, right? And then the prior guess, especially of value p equals to 0.3, actually becomes very less likely, because the data shifts to, I should say, 7.7-ish, right? The data tells us the percentage, the sample percentage is 70%, 0.7, and then we're able to see that effect contributing to the posterior. Okay, make sense? Yeah, so it's typical, it's a good practice. So here it's discrete because we use p, 11 different values of p, and then we assign specific probability for each of them, right? And so when we plot things, you can see like those dots and the crosses here and there to represent the discrete probability. But then soonish, you will see other ways to express the prior distribution for this p, which is continuous. But it's also it's always a good practice to plot the prior and the posterior together to see the changes. Okay? To see, like, at least to make sure that what's the effect on the posterior makes sense to you. Okay? For us, it at least makes sense, especially with the spike of the posterior of around 0.6, because that's what the data is telling us. Okay. All right, cool. So this is the demo that I was hoping to do. So now and then come back here. So the code is on Moodle, so feel free to access to it and play with it, especially with different values of p if you want to come up value just by yourself. And I mentioned briefly that the data model, which is y given theta, is a binomial, right? I should say, let me use a different notation. So we know that the y, probability of y taking a particular y value will be n choose y, theta raised to the power of y, and then 1 minus theta raised to n minus 1, right? Yeah, so this is actually the way that we compute the likelihood, or I should say the data, the probability of the data under theta, okay? So what we are doing essentially is for different values of theta, so theta is p, by the way, sorry for the different notation. So for different values of theta, we compute the probability of y equals to 7, and we use that as the data and then combine it with our prior to compute the posterior. So I will prepare something extra to show you the detailed computation, but it's pretty straightforward, and the R script that I showed you earlier was pretty much just doing all of the calculations through R, okay, and then do it quickly for you. But in theory, you're able to compute it by your hand. All right. Yeah, so eventually we were hoping to achieve certain analysis goals in general, not only estimate the uncertain quantities, which are the parameters, but we also want to, in the long run, not for today, in the long run for the course, we want to make predictions of future events. We can also do hypothesis testing in the Bayesian framework. We're going to talk about it as well, and then eventually also make decisions. So these are the goals that we're going to try to achieve this course throughout the semester, but everything is built up from what we talked about, the general framework of Bayesian inference, how you can specify prior, how you can come up with your data model, probability model for your data, And then how are you going to compute your posterior probability or posterior distribution? All right, so I will stop recording here and then